Hello, I am here to talk to you today about decentralized supply chain management and how to build software, any software at all, with Warpforge and the power of hashing. Warpforge is a piece of software I'm going to introduce today that is a build tool that you put other build tools in order to attempt to universalize things. It's going to worry about supply chains, the data that you bring into your build environments, and secure those by the use of hashing and hash tree data structures. And it's going to be a project that I hope will work for everyone. I want a project for build tools which is collaborative and decentralized and designed to help share information so that people can work together without being forced to work in lockstep with each other. Hi, I'm Eric. I won't go too much into my history, but the things that bring me here today to talk about building software is, well, that I do a lot of that. And I build a lot of different pieces of software for different organizations, for different projects, in different languages. And that experience is something that I want to be good. And as I work in many different projects, I accumulate a lot of maintenance work to do as well. So I'm really interested in having build processes and software that lasts. And I like to build software that other people can get into their hands and use easily, which also requires the process of delivery to be well paved. And so in this talk, I'm going to go into that and some challenges that I find with it. And I'm going to introduce a piece of software that I hope solves some problems around building other software. But first, I'm going to spend a lot of time on the motivations and some of the problems there. Some of the problems in building software are also quite difficult because they're the kind of problems where if you have a half solution, it turns out to be no solution at all. Those are tricky ones. So in this talk, I'm going to start with the norms now, and then further go into what we wish things were like instead. Talk about a few inspirational projects that I think have really good ideas that I'd like to bring forward, and then do some problem solving, introduce Warpforge and this new tooling that I'm excited to share. As time allows, there'll be some comparison to other projects, and then looking towards the future, what more work could be done, and how could people get involved. So, the norms today in building software. Building software is easy, right? We're a whole facility full of, a conference full of software developers, so clearly we know how to build software. We just all have to know what all of the tools are, every different tool for every different language, and every different project, which is totally fine, right? It's easy to memorize all of these things and all of their different features, and they all work exactly the same way, so it's really low cognitive overhead, right? No, I'm being sarcastic. This isn't true at all. There's a ton of memorization to do there. And all of these tools, they have the same level of reliability, right? Every package manager you've ever worked with has lock files, and they all totally work, right? They all pin exact versions and are highly trustworthy, right? Everything is versioned, right? No, this is not true. Some package managers get lock files, many don't. And then when we have prerequisites for something that goes outside of our immediate project, like something needs to depend on GCC, or other examples vary by language. For example, in Ruby, the Nokogiri gem is famous for being the easiest thing to install ever, right? No, none of this is true. When we have packages in our projects that depend on system level packages, things like C compilers are a frequent example, then these cease to be things we can automate. They become massive global variables, and I think I can't even really tell jokes here. Everybody knows that when we get to this depth, we're kind of hosed. Like, at that point, you start writing instructions in the README of your project instead of writing code for your build process, and you just sort of ask forgiveness for everyone who's ever going to come after you. It's a bummer. It's not great. But hey, once we have software that is built, at least it's easy to know exactly what happened and describe that information. So, if we solved the problem once, we can solve it again, right? Or we can even hand an audit log to somebody about what happened, right? No. No, that's not normal either, is it? Knowing what you just built the instant after you finished building it is, in fact, a madhouse. It is not normal for any of our build tools to help us have information about what we just did. Do your build tools give you hashes of the things they just produced? If they do, can you look that up and map it back to some other information, maybe some hash IDs of the source code that went in? Okay, maybe, but probably not. But how about then, can you map it back to all of the other dependencies used, or the compiler versions used? If you want to debug any of these things in retrospect and know what you've just finished doing, can you have that information out of your toolchain? And can you hand that to somebody else to reproduce, or to your future self next Thursday to reproduce? This is not normally provided by any of the tooling that we use. This is kind of out of control. This is just really disappointing. It's unproductive. There's tons of time wasted here, and it's also outright insecure. Attacks on software supply chains have become outright common in the last couple years. SolarWinds was one of the big headliners, but there are many more in history now. We have to get more rigorous about this. We have to start really versioning everything, and that just doesn't mean source code. Everyone knows now you have to have your source code in version control, right? That's obvious. But that's not enough. We need the whole systems. We need the entire package management chain and everything that goes into it to be secured these days. That needs to become table stakes. But where are we actually at? Nowhere near that, right? The best thing that we can do to maintain our build systems and our projects are tons of blood, sweat, and tears, enormous amounts of manual work. Maybe the best duct tape solution that everybody's got is we can bake these giant megalithic images using container systems. This is becoming popular now. But then you get giant container images. So, partial solution. Or really what happens a lot is we ultimately give up, right? We just sort of accept that none of our work can really be shared or reproduced. We start writing rough instructions in the README instead of scripts that actually do work and save other people time. This is pretty bummer. So, okay, but there was one possible solution alluded to there, right? Containers solve some of these problems around reproducibility, right? Sorta, but not really. We'll give credit where it's due. Containers tend to bring with it this idea that you're going to have a script to build stuff, and you're going to have some reasonable isolation, which means the script will be truthful and do real work. So that's progress. That's good. But what we do with that nice, clean environment is really pretty silly. The normal thing to do when you've got a container is to start with this nice, clean room and go invoke other package managers in it. It's the functional equivalent of taking a bucket and going outside the door of your nice clean room, scooping up whatever mud you find in the streets, and pouring it out in your clean room. This does not help us understand what we're doing at all. It helps us freeze that thing. Once you've done it once, you can snapshot things with containers. Maybe that's some kind of progress. But think about all the things that it doesn't help you with. It doesn't help you reproduce that container at any point in the future. If any of the package managers used inside of it lacked any kind of lock file, and they probably did, you've made no progress at all. They don't help you update this container. They don't help you maintain anything in it. You've gathered all of your maintenance burdens into one big image and you've frozen them there, but now you just have that one big image. And did that help? Because now if you want any of the rest of your build system to be reproducible, you just have to hang on to that image until the end of time. Hooray! And it's huge because it's the whole system, right? So now you have this huge image, plus now you get to start dealing with container registries. Wonderful, a new totally online single point of failure. Fantastic, just what I wanted, right? No, not what I wanted. There's no progress at all. If there weren't lock files inside the things you used in the container, then we haven't advanced our journey at all here, right? And with some of the most popular container systems, you have this idea of like a linear stack of layers in which you do one unreproducible thing after another, and somehow that's going to help, and like, it doesn't. And now people just spend massive amounts of time trying to make sure that cache invalidation somehow yields productivity, and I don't think I've ever seen somebody win at that battle. And in exchange, these huge images, they might have actually made things worse. You can't explain these images at all once they're fully baked. Like, you can try to build security scanners that trawl over them retroactively, but like, this is a losing battle by the time you've even begun. They're not helping you upstream fixes into anything you've baked into this container, right? There's no road to doing that. If anything, you've made that journey farther than when we began. And from their sheer size, it makes these images hard to share. If somebody else has anything less than exactly the same dependencies as you, now you both just have these multiple 100 MB bundles, and you can't share them. Like, heck, this is making it harder to work together. And then at the end of the day, people just sign these images, and we have to ask ourselves, what are we signing when we do that? What does this signature mean? Hooray, I scraped a bunch of things together once, but was any of the process that I used sensible? Was any of it reproducible? If I myself ran the same process again on Thursday instead of Tuesday, will it work? I probably don't know. So the norms in all of these things are that we're just kind of slamming stuff together and hoping it works. Our best current defenses against any kind of supply chain issues and our quest for basic stability, our best weapons might be containers and CI pipelines. But they're not actually fixing any of the underlying problems, and by being so monolithic, they might actually be making it harder for people to collaborate on these problems. So, in summary, I want to learn from the best stuff that we can do here, but it's time to also look forward in some new directions, because we haven't solved all the problems. And one thing that should be indicated to us, I think, is that solving these problems of package management and supply chains piecemeal is not going to work. The best leap forward that we've taken so far is with this container technology, where we admitted the whole system nature of the problem, and that is a huge step forward. We need to have better solutions still, but that was a key step. I think we need to acknowledge that to make the world better, we need tools that are going to guide good behaviors. So right now, our best option for that is, I'm not sure. Containers give us no guidance for making better, more reliable tools. They're just a huge Band-Aid, right? It's not helping. And I think our current best defenses against non-determinism should indicate to us that snapshotting is necessary, almost certainly, but it's not sufficient. So let's look at, try to make a brighter image in our minds of what things should be like. If we had the perfect tooling, what would it be? If I wanted to build anything and be good at it, what would be the attributes of that tooling? The fundamental thing that I want is a tool that is intensely predictable. If I have set up a build pipeline for something once, it should work forever, barring the end of the human race and our ability to manufacture silicon. There's no reason we shouldn't be able to solve these problems. We have lots of things that are very endurant. If you have a Git repo, you can reasonably trust that it's going to continue to exist basically forever, right? You do need to mirror it. There's a basic availability issue, but you can be very confident that you're doing so. If you've got the root hash of that Git repo, you can replay it on any storage everywhere forever, and this can be a very solved problem to make this permanent, right? I want build tools like that. Very predictable and very easy to replicate. I want a build tool that brings that stability to everything else it touches. The tool needs to control the supply chain of other pieces of information that are going into it. If we want predictable results from the output of the process, we need to have a predictable control over the supply of the data that goes into the process. If we're going to have really good tooling for this sort of thing, I want it to work for anything. Now, that makes the problem pretty mountainous, but what that means in practice is I want a tool that brings together other tools that already solve build problems in some domain, some particular language, for example, and I want to let those tools do what they do best, but putting them in a sandbox where we can help them with the supply chain problem. Towards that end, I want a tool that can assemble things freely. So in any build process, there are several inputs. I almost certainly have source code. I almost certainly have compilers, for example. And probably the list hasn't stopped there. It's very likely that I also have some kind of shell scripts that are gluing things together, or other tertiary tools that are helping orchestrate the build process. Maybe I have a make file. Maybe I need the make dir command somewhere inside that. There are several other things in the environment that are needed. I want to be able to assemble those things, but also without baking them together in perpetuity. Needing something in the build process doesn't mean that I need to ship it later, and it doesn't mean that I should be gluing them all together into this mega image sort of thing that creates a burden for me to carry on in the future. I just want to plug those things together and have them mounted quickly together, use them, and be done. Ideally, I want my build tools to be local first. And maybe that's kind of obvious, but I think this just really has to be said. I want something productive because it starts on my machine with resources that are right here in my hands. Sort of in the same way that Git is very immediately productive because you go Git init and there are 0 network operations. I think that's an essential quality in good tooling. But I also want a tool to help me manage software builds that's fairly social, because there's a lot of software in the world and I can't build all of it personally. I can't maintain the build instructions for every single thing in the world. That's too much. So I need some tooling that helps me exchange and coordinate work with others. This could be at the scale of some sort of industry working group, like maybe my team or another team down the hall, or it could be at a much bigger scale of like, I am an open source project that needs to collaborate with an entire swarm of people who is building like large suites of software, maybe even a whole Linux distribution, for example. I want to be able to coordinate that and do it in the open. So that means concretely, monorepos are not an acceptable prerequisite for a functioning build system. And I don't want to end up in a situation where I'm just hucking huge images over the wall. And I have one more bonus goal. I want the system to come with a determinism detector, which functionally means I want hashes everywhere. I want something that lets me rapidly see if the work I am doing is stable, deterministic, and reproducible. Because if you can't measure it, you have no idea how to improve something. So let's start measuring. And then always the thing you need from any piece of tooling is for it to be easy enough to use that it can become widely used, so that it can be the path of least resistance and really gain adoption. So that's just always the goal, right? So that is a lot of things that are needed. But it's possible. So in order to get some positive inspiration, let's talk about some stuff that is good. There are 2 pieces of software in particular I want to call out and grab some good influences from. One of them is Git, and one of them is Make. What's inspirational about Git? You're talking about build tools. What is this even doing on the screen? Git isn't a build tool. Okay, true. Git is not a build tool. But it can still be very inspirational, because Git is this beautiful example of local first stuff and the huge productivity therein. I already kind of pointed at this. Working in the local file system first is just so productive. It means you can get started without asking permission from some other group or service that might be online, centralized, and maybe is difficult to contact and coordinate with. Git is also a very clear pointer for why a good system needs hashes in order to deliver these features and this productivity. Having hashes deep in your system design means that you can always talk about exact contents without necessarily having to invoke human readable names, which means you don't have to choose human readable names, which means you don't have to argue with anyone about human readable names for your data either. This is a really good thing. You can add names into any system with hashes on the bottom later, and Git is also a perfect example of doing that very successfully. You can use branches and tags to label things in Git. And that doesn't take anything away, but having the hashes on the bottom makes it all stronger, because now if you ever need to do conflict resolution, right, you can point at the 2 hashes of different content that's conflicting. And this lets you do resolution while still being precise. You can have arguments about the human readable names without losing track of what's fundamentally going on. Very valuable properties. So I want to copy this. I want to be inspired by this as we do build tools. Lots of hashes will make things able to work in a decentralized way, be productive, and be very concrete and stable. Okay, the other inspiration, Make. Make is pretty ancient, but it has really good ideas embedded in it. One of them is that it works with anything. It lets you coordinate other tools. And I think this is one of the key contributors to the longevity of Make. It's never really gone out of style. You see Make files still in modern projects because it's good at doing a few things and then coordinating other tools that do lots of other things. So it always is sort of keeping up to date by not doing too much. It's also got a graph of targets. It lets you build related graphs of tasks, and this is a good feature. But it's not a perfect tool also. It shows its age in some ways. If we did it again today, probably you wouldn't write make with the same interesting domain-specific language with which it is implemented right now. Tutorials for make are a bit bumpy for most modern readers. And make also did not make any attempt to solve external dependency management, which is a pretty solid choice at the time that it was first written, but it's pretty obvious these days that everybody's software depends on everybody else's everything, or at least quite a few things. And we do need fetching tools. Like, this is a problem that needs to be solved. We need supply chain management. So make has some great inspirations in that it binds other tools together in productive ways, but also doesn't solve every problem. So let's take these two good ideas, these two key influences of Git and make, and take the best parts of them. Combine that also with the idea of container isolation, clean rooms. And maybe let's put a nice programmable API around this, something simple and standard like maybe a JSON API. And then can we get build tools that are awesome? I think, yeah, let's do it. Let's make a build and supply chain manager. Let's make tools that make our lives easier by being predictable. So now I'm going to offer you a piece of tooling which has attempted to do that. And I hope it's either immediately usable or inspirational. Warpforge is a build tool. It is the kind of thing where you cd into your project directory and then say Warpforge run. It's going to look for some declarative files in that directory that do stuff. So for example, the JSON in there has no funky DSLs, by the way, just JSON. Has an actions section, and it can include shell scripts or any other kind of actions based on this sort of idea. These declarative files can contain multiple steps, which can be related together. And because we are so interested in stability and predictable tooling, Warpforge enumerates its inputs by hash. And by the way, you can compose them. You see, this is just a plain JSON map, and you have paths that things will be mounted at, and then you have a content hash. Wait, what? Perhaps you're saying. That's awful. That is not going to be easy to use. That's going to require you to copy and paste a bunch of totally illegible schmutz, and it just will not be good. No one will use this. OK, that's fair. That's true. So we've set ourselves up a problem here by having hashes in the middle of this API. Having hashes in the middle of an API creates serious ease-of-use challenges. So we'll have to jump over that gap again. I think the answer is be inspired by Git. Git did this, right? Lots of hashes, but add names on top. So in Warpforge, we're going to try to copy that. Lots of hashes on the bottom, and then additional layers that bring naming back on. So you have this sort of set of levels you can traverse from precise to easy to use. So Warpforge will support name lookups as well. This is roughly the same structure. There's a map here that's got mount paths in it, and then it's got human readable names. Now this is going to be really tricky, but these human readable names, we still want them to be reproducibly resolvable, work fairly decentralized, work local first. How are we going to do that? More inspiration from Git. It's just always, do what Git did, then do it more. Imagine that in the same way that Git branch names refer to hashes, that's fundamentally the same problem we need to solve, human readable name to hash. But now let's take our mappings there from name to hash, and we'll put that in another Merkle tree itself, so that you can easily version this and easily fork it, have a local copy of it, do whatever you want in roughly the same way that you would fork and copy and make Git repos be local for productivity. Also, Warpforge will let you save whatever files you want. When you write one of these declarative scripts about stuff to do, we are going to run it in a containerized sort of an environment, but we're going to let you say which file system paths you want out. This is probably pretty obvious, but given the history of containers, I feel like it's important to say, you're not going to be stuck with full system images. You can say, give me the outputs from /, and then you will get a full system image. but you don't have to. You can be more precise. So we use a series of layers to separate these different levels of functionality. I'm going to go over those now from bottom to top. At the very bottom, of course, file system snapshot hashes are something that we need in order to even start the discussion. In Warpforge, we call those where IDs. Then we have an API object called a formula, which is a task declaration. You put your shell scripts and whatnot in here, and you list all of your inputs and your desired outputs. But a formula is only allowed to use hashes. So this is a very precision and stable-oriented API concept. The idea is if you have a formula, it's something you can evaluate and expect a deterministic result out of. But as we've already said, hashes alone are not human-friendly. So in order to get work done, we introduce another API layer above this, which is called a workflow. And in these, you're allowed to use relationships that are constructed using human-readable names for references. But using human-readable names is treacherous, as we've already mentioned. And so now we'll introduce one more system called a catalog, which is going to solve this problem. We really want the human-readable names, wherever they're used in the system, to be reproducibly resolvable. And we also want that to work offline, like without any central authority necessarily. So here we use essentially a decentralized database that is stored in a Merkle tree, much like Git itself. This solves the name lookup problem. And now, I'll show actual examples of the size and scale of JSON on the next couple of slides, by the way, just going up the stack first. You can write this workflow object as JSON, and it's OK. If you're going to write a couple of projects, you're going to manage a few builds with this, you can write the JSON by hand, and you're going to have a fine time. But if you wrangle tens of projects, you're going to start seeing some repeated elements. If you wrangle hundreds of projects, you're going to start seeing some very repeated elements. And if you wanted to build an entire Linux distribution, maybe you're now going to stare down 25,000 packages or something as a normal number in that environment. Now you're going to see a lot of repetition, and you're going to have some maintainability needs. So for this, we have one more layer yet, which is called build plugs. And this is where we introduce a whole programming language to let you solve the reuse problem. A build plug is something that does any computation you desire in order to template a plan, and then emits this as JSON, and we will turn around and use it as a workflow. So we have all of these different layers in order to solve different problems with different levels of power and flexibility. At the highest level, you can do anything at all and use Turing-complete languages to generate any kind of a plan that you want. In the medium level, we have reproducible solutions for name lookup and build instructions that can have multiple steps and connect things, but are still purely declarative. And you can walk across workflow JSON with no need to compute, for example. And at the lower levels, now we've substituted in names for hashes, which is a wonderful thing for debugging. When you're holding on to a formula object, you know exactly what you've got. And at the lower level, yes, of course, we just needed file system snapshots. So you can write high-level stuff and get tons of hashed auditable checkpoints out of a system with this basis. OK, I have to at least briefly flash JSON on the screen, just to be credible here. So this is what the lowest level objects look like in Warpforge. It's just JSON. You can see perhaps that there are hashes in the inputs, because this is the thing that is made for precision. And when you evaluate a formula in Warpforge, you get this JSON object down here, which has more hashes in the outputs. So now already you could use this single step thing in order to glue it together with a series of bash scripts and JQ pipelines and stuff, and you can make a whole build pipeline. But we're not going to force people to do that. That's what workflows are for. This mid-level thing that's a little more expressive and lets you connect things with human-readable names. This text is certainly too small to see. Not the point. You don't need to read it. I just want to emphasize that this is JSON. It has the nice flowing curvatures of JSON. And this is something that you can produce mechanically, read mechanically, and so on. It is also a real example of a workflow. This JSON happens to be for compiling and packaging bash, which is something we've done in Warpforge just to prove that we can. The one thing I will zoom in on there is what it looks like to connect things. Where you are importing stuff from other workflows, there's this syntax that refers to catalogs and has human readable names. This is the thing that will resolve against that Merkle tree database. And workflows, because they can have multiple steps in the same workflow, when you refer to another one, this uses a syntax of piping and then a step name that is a sibling, and then naming an output within this. So this can produce whole graphs. And then, if we want less than 1 million miles of JSON, this is an example of what one of our build plugs looks like with a batteries included system that we've made, which is based on the Starlark syntax. If you're not familiar with Starlark, this is actually something we're borrowing from the Bazel project. It's a very good invention. It's essentially a Python syntax with a nice self-contained interpreter that's easy to ship and has no system interactions. So very nice tool. This happens to generate the workflow that was on the last slide. So you can see it's a fewer lines, and it's allowed to use libraries loaded from other files. So this is an example of how we expect reuse to work in this system if you have a large number of packages you need to wrangle. Now that catalog thing, this is the name lookup database. Catalogs are really just a series of files with more JSON objects in them. Everything here is API driven. So a catalog is what we call the total set of all information and releases that are tracked. It is full of a bunch of modules for different projects. Each module may have many releases, and each release may have many items. Items are used for like architectures and stuff. So if you have one of these string tuples that names a module and a release and an item, you can look that up to get the hash of a where ID, a content snapshot ID, or some metadata attached to it. This entire thing can fit itself in a Git repo if you want to have it versioned in this way. That makes it very easy to vendor also. You can put it in a file tree in any other Git repo. And it has its own built-in hashing scheme as well. Catalogs are a Merkle tree, as I have alluded to. So the logical structure looks sort of like this. There's a big old tree in there. This should probably remind you of Git at least a little bit if you've seen diagrams of the internal layout of Git. Catalogs actually point at two things, by the way. They're solving the naming problem for looking up content hashes, like the actual file system snapshot IDs. But we also store some metadata in them, and that includes a copy of the workflow used to build whatever we've just released. Now this is optional, but it's default, and it's a very useful attachment. This means anytime you look something up in a catalog, you can turn around and go fetch that file set because you know what its content ID is. Or if it's got the workflow used to build it attached, you can go do that instead. You can trade bandwidth for CPU time. You can replace anything, assuming it's deterministic. So now about that collaboration angle, that social angle for this tool. I said earlier, I want to work in public. I want to be able to collaborate with other people at various sizes of team, at various scopes of relationship distance even. So how are we going to do that? And how is this tooling relevant to that? The catalogs are really key here. Now, forgive my diagramming. It is a little rough. But the key concept in this system with the catalogs is that they are letting you do checkpoints around any workflow. You can describe one workflow that's doing some set of steps, and it's using catalog references to look up all of the inputs, and when you produce something on the end, you're putting in another catalog reference, as well as the workflow, right? So if I want to build something at the end of the diagram here, I can look up the workflow that does that. I can fetch, I've got serious cursor lag here. Maybe I will not try to point at the diagram too much. You can fetch other contents that go into that, and you can build them if you want. You can also choose not to do that. You can just drop off some parts of the graph. You can lift out some parts of the build graph and do just those by fetching the content snapshots that are the inputs to that. If you want to recurse into building other stuff leading up to it, that's up to you. You can make this choice on the fly because of the way we point at both content IDs and rebuild instructions. This means like the rebuilding is optional. This is different than most other tools I've inspected in this space, so it's kind of a big deal. And now also I have to pause for a moment and backtrack to something that might be bothering you if you've been watching carefully this whole time. I had these examples of input file systems mounted at arbitrary paths, like /foo/bar, whatever you want. And you might be thinking, that's not right. That's not how computers work. You can't do that on Linux. Programs have to be mounted at specific paths. You're going to have like library linking hell here, right? It's not going to work. Install paths, prefix paths, those have to be set at compile time. What are you doing? What are you saying? This composition is useless because nobody can ship software like that. Well, yeah, we can. This is a problem that we have found in the process of developing Warpforge, and I'm going to have to say that we've also fixed it. I have to tell you about my plan to destroy all Linux distributions. No. My plan to bring about the year of Linux on the desktop. Well, we'll see. But at the very least, I have a plan to make things easier to ship by making them less entangled. And it's called Zaps. This is kind of a side quest from the main track of the talk here about build systems, but it is sort of an important one because it lets us do this composability stuff. Zaps are a way to package Linux software. It's short for zero dependency applications. Zaps involve bundling all of the libraries into one file system, perhaps sharing them as one tarball. But once you've done so, a Zap works anywhere. It works at any path. It works without install hooks. It will work fine even on a read-only file system mount. So this means if you've packaged something as a Zap, you have solved building and shipping the thing. You can give it to anyone on any Linux distro. They do not require containers to run. They do not require chroots to run. They don't require mounts to run. Absolutely nothing weird. They are regular Linux ELF dynamically linked executables. They even work on BSD, crazy fact. And this gives us the ability to mount anything, anywhere, and be freely composable. It's very cool. But I won't spend any more time on that in this talk because there just isn't that much time. However, if you're interested in this particular topic of how to ship software to any Linux, there's a website, zaps.app. And you'll find some prior talks recorded in that website as well, and a bunch of documentation about how to go about this. But for now, trust me, it's a thing. It works. So let's look at some of the nearest comparable build system projects. People have tried to build software before, I dare say. So there are some projects that get close to similar. There are lots that aren't comparable at all, right? If you're a single language package manager, you're solving a much smaller scope of problem than I'm talking about here. If you're a single Linux distro manager, you have grappled with a big problem, but you've also decided that you're going to solve it for just your community, so it turns out a little different. But there are some projects that have been similarly ambitious to what I'm describing with Warpforge. They've tried to solve building everything in every language, and they've tried to solve it in a non-denominational way. The two that come to mind the most here are Bazel, or Blaze, from Google, and Nix and its variant Geeks. Gwix? Geeks. I love the pun there, honestly. So, and I put a slash between these because Nix and Geeks, they use like much of the same internal tooling, so they're very closely related. I'll mostly just talk about Nix for simplicity. So these are both tools that are trying to build everything, like I said, so they are comparable. The main difference is the shape of the dependency graph. So I'll go back to this diagram. This is the graph that I drew for Warpforge stuff. We have our workflows, and they depend on these checkpoints where the catalog is used to look up specific content IDs. And so we've got these detachable graphs here with the catalog as like a mediator between subgraphs. If I try to draw a similar diagram for Nix or Bazel, I come out with something very different. This is as topologically close as I can drag these together. You see that there are 3 things being built and like roughly 5 inputs. So this is as close as I can get. But what you get with Nix and Bazel is they have build descriptions, what we would call workflows in Warpforge. Nix calls them derivations. Everybody's got their words. They've got a thing that does stuff. And in Nix and Bazel, the build instructions depend on other build instructions. In Warpforge, they depend on catalog references and content IDs, right? In Nix and Bazel, it's just on other build instructions. So they don't have that checkpoint. In fact, this causes users of Nix and Bazel to be on this continuous quest, almost accidentally, to bootstrap things, to like always build one thing deeper into the dependency tree. Which is not necessarily a bad thing inherently, but the fact that they're kind of stuck doing that by the nature of their tooling is maybe not ideal. And so ultimately, at some point this has to stop, right? At some point you have files that were like there at the beginning of time and you build up from there. And in Nix, that's called a fixed derivation, where instead of having a build instruction, you have a fetch from the internet instruction. But they can only have these in the very farthest leaf nodes of the tree, which is kind of strange. And they have no ability to put these in the middle of the tree without rewriting it. In fact, there are hashes used, my favorite API structure, a hash, right? It is used in Nix in order to identify derivations, their build steps. But the hash that identifies the derivation covers all of the other derivations, all the other build instructions that it depends on. Which means if you change anything that it depends on, you've changed the ID of this thing. And so it means if you try to substitute a fixed derivation into the middle of a dependency graph where you previously had build instructions, you've changed the whole graph. It's really weird. So they can't freely at runtime choose to fetch or build. Now, if you're really highly knowledgeable about Nix, you also know that I just told a fib. There's a mechanism called substitutes in Nix, in which you can fetch content instead of building it. Except you don't know what you're fetching anymore. The substitutes mechanism in Nix just sort of gives up on the predictability of this. You ask a remote server to give you a substitute for this build step, and the remote server promises that the content that it gives you back is related to what you asked. There is no verification pathway for this. Oh dear. So, this concept of a catalog in Warpforge really makes the whole system distinctive. It lets you choose what you want to do at these checkpoints. Do you want to take literally the content that has been recorded in the catalog, or do you want to recurse on the building? It's a free choice. This also has some other more interesting topological implications that don't come up too often, but I have to talk about this because I think it's cool. Warpforge can describe things that build themselves. You can have a hash as one of your inputs that is produced by the same workflow that's consuming it. This is impossible to describe with these other systems where build instructions depend only on other build instructions because you can't describe it, it's just not there. This doesn't come up too often, but it's interesting when it does, because this is what you should hope your compiler bootstrap looks like, right? Your GCC build ought to be able to produce your GCC build again. If not, do you know what your compiler even contains? This is sometimes called the trusting trust attack or the Thompson attack or the defense against it. I think if you can draw cycles like this in your build graph, you've just defended against it. It's a good thing. So there are some other differences, some smaller, finer-grained ones between Warpforge and these other systems. The big one is the content address checkpoints, right? It's a huge thing. There are some smaller differences too. So Bazel, for example, has a lot of magic built-ins for the different languages that it supports building stuff for. Warpforge doesn't. Warpforge just gives you containers and shells and lets you figure it out. I'm hoping that this less magical approach will help keep things simpler. And I'm hoping that the content address checkpoints thing will help Warpforge build much bigger ecosystems, whereas Bazel, in practice, if we observe where it's been adopted, it seems to be mostly monorepos. I think that's a pretty uncontentious observation. And my guess is that this is because of the build instructions depend only on build instructions and the bootstrapping quest that comes after. I think the content address checkpoints might help us get away from that and share more work and hopefully be more adoptable. Warpforge versus Nix, similar very much to that story about Bazel. Also, Warpforge and Nix differ quite a bit in that I've showed you almost entirely JSON for Warpforge. Or there was that Python-like syntax if you want it. Or that entire level of the system is easily pluggable, right? Bring your own templating. Nix is programmed using something called the Nix language. And I'm going to say absolutely nothing about this other than you can read lots of other people's opinions about the Nix language online. I will let the gap there speak for itself. So Warpforge is aiming for easy to use. And again, I hope these constant address checkpoints help us build more collaborative ecosystems with lower coordination. And we also have this Zaps thing. So Nix builds a distribution called NixOS, in which they have a huge amount of software. It's a very impressive collection of work, but it is a distro, make no mistake. So when you install Nix, you get a series of paths, all starting with /nix on your system, and then the whole distro goes in here. With Warpforge, we introduced this Zap concept, where you package the entire application in a way that works out of any path once you've unpacked it there. And so our goal with Warpforge and Zap's packaging is to make stuff work anywhere. We want to be able to export our progress from Warpforge and not have it depend on Warpforge. I don't need to be the dependency of everything at runtime forever, right? I don't want to be. I just want to produce stuff that works and give it to people as quickly and simply as possible. So my hope is that with this low dependency, even zero dependency application packaging format, we can build more than just another distro. We can build pieces that anyone can use and just have an end to distro distinctions. But there are good things to see from these projects. Bazel and Nix and Geeks and these things. They are good inspirations because they prove that it is possible to take an ambitious stance on this problem of build everything and to deliver on it. Like, these are real projects with like pretty sizable user bases. It is possible. We can also observe, however, that offering a plain JSON API is, surprisingly to me, going to be a novel feature. Nobody's done this before. If you want to interact with Nix, you kind of have to use the Nix language. If you want to interact with Bazel, I said we borrowed that Starlark language from Bazel, but that's the only way you can interact with Bazel. Like, that's the API. They even generate other Starlark files. It is an interesting way to go about things. I like JSON. I know what JSON parsers are. I've got a lot of JSON emitters in my like suite of libraries. It's a thing I can work with. And we can ultimately also see that there's a real usability challenge in making it possible for people to collaborate with these tools without dragging them together and getting them stuck in lockstep. A lot of these build tools that have tried to solve the build everything problem end up getting stuck working really only in monorepo environments. And I'm not going to say monorepos are bad, but I don't want them to be the only viable option. So we've tried to learn from all these things in Warpforge, and I hope that we offer real improvements. So, what does the future contain? Tons. Warpforge is an alpha level of project. We've shipped core tools that work and demonstrate the real promise here, but they are very rough. We have shipped several dozen real packages, everything from Bash, that I had on the screen earlier, to Vim and Emacs, believe it or not. So we're getting there on bootstrapping stuff, but tons more to do. We have a prototype of using these templating systems, such as the Starlark one. It's very cool. And we have some other features like a tool that takes the catalog Merkle tree, this giant named hash database, and exports a nice shiny website from it that you can easily navigate, including clicking through the replay instructions on the fly. So that's cool. But there are tons more things we're going to need in order to make the system really sing. Many, many more packages, certainly. Bridges to existing systems to make it easy to take whatever language and ecosystem you're working in now and access it in Warpforge. We're going to need a lot of this. And I think a huge ecosystem of tools like automatic rebuilders that verify determinism, automatic version bumpers for things, like Dependabot style things, are all very much going to be needed and are future work at this time. So if you've watched this and you are thinking, okay, I'm in, how can I help? I'm so glad you asked, because it will take a village. Technology is great, but it's not enough. I hope that this Warpforge tooling that I've talked about here is going to provide a good foundation, or indeed just plain inspiration if you want to do something like it. But technology is not enough. Whatever we do here to improve the state of build tools has to meet people where they're at. It has to be easy to extend whenever there is a gap between where they're at and where we want to be. And building a lot of software truly requires building a community that pushes that process forward. There is too much to do for any one person or even any small group of people. The world has tons of software and it needs tons of people to build and maintain it, even with high leverage tooling. So, in the spirit of extensions, I want to talk quickly about a couple of places where we made Warpforge ready to extend in order to meet needs that we might not yet have anticipated. So, I should have put a real hash in there. Imagine a hash on the end instead of a keyboard smash. Where we have input file systems and snapshots and where IDs, this is actually a plugin system. If you saw the demos earlier, they had tar : some hash, and you also saw git : a git hash on the screen. That's a whole set of plugins. Git and tar are the ones that we use the most, but if you would like to support other systems, we have a nice corner of the code base where you can introduce those things in an easily extendable way. Where we have actions, the one you'll see most commonly is called script, and it means we're going to run a container, use a shell, and then pipe some instructions through to that. But this is actually another plugin point. Where the word script appeared in those demos, we can introduce other keywords here, which could invoke other kinds of executors, if you will. Maybe some of them won't even be container-based. Maybe it's time for a WASM plugin soon. If somebody would like to contribute that, I will happily show you the path to that part of the code where you can do so. We have this build plug stuff, the templating engines. Right now, we have shipped an early prototype of this system based on Starlark as one of our build plugs that is batteries included, because we want to have something available right out of the box. But we have not yet developed a huge set of libraries and conventions about how to do various build instructions in it. So there's tons of future work to go there, and people with strong opinions would be highly welcome to contribute to this. Or if you just hate Python syntax, you don't like where the parentheses are, you truly can build your own build plug system and bring it into this system. The way that Warpforge interacts with build plugs is probably one of the easiest places to extend right now. It is literally, if you can give me a command to exec, and it returns JSON on standard out, that'll do. We will evaluate that JSON as a workflow. Very simple extension point.
Can I use Q?
Can you use Q? It emits JSON on standard out, so yes.
Well,
why not? Great. There's another concept that I hand-wavingly call Bifrosts as just a grouping term for bridging to other existing package ecosystems. I think there's a lot of future work to do here, and I would love to hear from people about, like, how shall we indeed take NPM, embrace it, and make it easy to refer to NPM contents via catalogs? Or, like, bring other systems' lock files into, auto-translated into Warpforge workflows. And anyone who is willing to package anything at all, if you are just joining us in building stuff with Warpforge, you are certainly helping. So, if you have time and the interest in hacking on this, these were some of the extension points. Come, hack, and I will be really happy to guide anyone into how to help if you would like to do so. On the other hand, if you're watching this and you find that you have no time at all, but you do have some sort of a budget, I feel obliged to mention Warpforge is a 501c3. This is the magic number in the US for being a foundation that is a nonprofit entity. So we will happily accept any charitable contributions and try to route it to other people who can contribute their time and skills and make sure the project goes forward. And to encourage either of those outcomes, I would like to remind you, if you build in Warpforge and you package with Zaps, you produce artifacts you can immediately use anywhere else. On your local system, you can plug them into your other container pipelines. It doesn't matter. They're deeply portable and not attached to the system in which we built them. So I would hope that this makes Warpforge a very high-value place to invest because it goes anywhere else afterwards. If any of this stuff interests you, here's the whole suite of links that you will need to find out more. The project website itself, you can find links to the community chat in there. If you like source code, there it is. And if you would like to see the catalog website, which contains several of the packages that we've already produced for Python, Bash, Vim, Emacs, etc., catalog.warpsys.org. Or the other GitHub link right below that is the huge Merkle tree of JSON files, which is the raw content. So that is the end of the talk that I have. Q&A welcome, or you can find me afterwards.